right, so what I was going to do today is talk about the harmonic oscillator and a little bit on scattering. This is sort of scattering in 1D. And the idea here is we again set up our sort of potential and our energy. And for these scattering ones, you typically have this region 2, right? So we have these 3 regions. 1 and 3 are the like asymptotic regions, meaning they're like at plus and minus infinity, they're far away. And we either shoot in particles or we receive particles, we detect particles far away. And that's comes up a lot in physics where you look at, you just have some region that's far away from your sort of region 2, which is like the region of interaction. It comes up in quantum field theory too, where you look at asymptotic states that come in from infinity as sort of plane waves. They interact, and this is how 3D scattering would work. You would come in with some plane wave from far away, it would interact with some localized region in space, and then you would see what happens to the scattered portion of your incoming wave far away. And both the incoming and the outgoing portions are kind of far from the potential, that actually does the scattering. So a very similar thing can be set up in 1D, right? You have far away, you have 0 potential here, and here you have 0 potential. And in the middle, you have something. And maybe for now, we would just put like I don't know, we'll just make it flat, and just make a little finite well. But it could be anything. It could be some wiggly thing. I don't know. It's some kind of interaction potential. But for now, we'll keep it flat, just as an example. And if we're looking for scattering states, right, that means positive kinetic energy. So it's sort of, we have to have positive energy here above 0. So these are the kinds of states we're going to be solving for in the Schrodinger equation, and we know what they are already. We have the 3 regions. In region 1, you have e to the ikx plus b e to the minus ikx, and this is the incoming part. This is the reflected part. In region 2, we would have some other coefficients, and since it's flat, and the energy's up here, we have same kind of solutions, except it's k prime because it's got a bigger kinetic energy here, right? The potential is lower, it's negative. So you just get a different k for your oscillating wave. Region 2, and then region 3, you again get the incoming and outgoing waves, the free particles. That's what it would look like. And for the most part, these guys are kind of fixed for any scattering problem, in the sense that all the kind of exciting stuff, the interaction happens in region 2. And here we have a very simple interaction with just a flat potential. But in principle, again, you can make something wiggly or something more complicated. And while the asymptotic regions are always going to be just these plane waves, right? Because out here, you just have a free particle that, either made it past the interaction zone. It's another way of thinking about it, right? You could sort of bracket off region 2 as a kind of interaction zone where complicated stuff happens and the particle either escapes or gets reflected. So that's kind of the setup for scattering. It's quite similar in 3D, except your sort of asymptotic states are everywhere around some finite region in space. And the asymptotic states are useful because we can think about trying to connect these coefficients to these ones and try to see if we can calculate things like reflection and transmission probabilities using kind of trying to minimize basically the effects of the complicated interaction zone, right? Which is there, it'll be difficult to solve the Schrodinger equation. So maybe we can sort of treat it effectively. Like we know that in the end, what's going to happen, either a particle is going to, come in and turn back around, or it's going to go straight through and get transmitted. So in the end, all we're really interested in is the reflection and transmission probabilities. And of course, they'll depend on the details of the interaction zone, but maybe there's a way to think about them in a nice way where it doesn't rely too much on the details of what's going on in that interaction zone. So that's the kind of the theme of the S matrix. You might have heard of that before, but that's the sort of why it's useful and why people think about it. And in the one-dimensional case, it's kind of easier to understand. So first of all, what will we do if we were to solve this, just by brute force, right? Well, the first thing we would do is we would match, right, between regions 1 and 2. We would match the continuity of the wave function and, its derivative. We would match those things. And in the end, we would get some relationship, a linear relationship between the coefficients A and B and the coefficients C and D. And we can write that relationship as a matrix multiplication. And why is it like this? It has to be like this because the Schrodinger equation is linear, so that if you combine, a linear combination of two different solutions, right, then the transformation between the coefficients in region 2 and region 1, they have to work the same way for, both pieces of the linear combination. So this is from the linearity of the Schrodinger equation itself, which I'm just going to write as, the Bras and Ketz. So it has to have this form, has to be a linear transformation like this. And it's got some properties. This is a matrix that tells you how to connect these coefficients to these ones. You could work out what it is explicitly by matching, at the boundary between region 1 and 2. But we can say some general things. First of all, if psi of x is a solution to the Schrodinger equation, I'll just write it schematically. H here is all those derivative operators. Well, then psi star is also a solution. And it's easy to see because you can take the complex conjugate of both sides of the Schrodinger equation. And since the potential is real, right? Yeah, we work with real potentials. Then the Schrodinger equation just, it works for psi star as well. That means that, what does it mean? If psi star is also a solution, then it should be the same matrix, right, that transforms between the coefficients of psi star. And if we think about putting a star here, what happens? Well, if we put a star, then these guys become starred, right? The coefficients all become starred. And there you get the minus I here, all these flipped signs, the little e to the I kx's. So what does it mean? It means that, and if we look here, it means that A and B will reverse roles. The B will be the one associated with plus IKX, and the A is the one that will be associated with minus IKX. So what has to happen is if we replace A with B star, because that's the new coefficient out in front of the plus IKX, and we replace B with A star, then it must be the same matrix that connects these two things. And these must be connected to D star, C star. Because psi star is also a solution to the Schrodinger equation, so the solutions must match in the same way across regions 1 and 2, for example. And so what does it mean? It means that the only way that this can be satisfied, is if the coefficients satisfy R11 star is equal to R22, and R12 star is equal to R21. You can take the star of both of these guys and then compare it to this top equation, and you'll find that you'll get these two conditions, that R11 star has to be equal to R22, right? Because it flips the A and B, so then this guy starred, R11 starred, has to be the same as this R22 in order for these two equations to work, and to be, you know, to be valid equations simultaneously. So you gotta, yep.
I do have a question.
Yeah,
so you flipped the A and B because we took the complex conjugate of it and we changed the negative to positive, and that's why. So B is now positive, and that's why it's on the top.
Well, it's not B that's positive and negative. It's these either the IKXs flip roles, right? When you take the complex conjugate,
Right. Yeah, that's what I was just wondering.
Yeah, exactly. And so we could take the star of this again, and then you'd get stars everywhere here. And then this would become BA and DC. And then if you compare it to this, the only way that those two equations can work is if this is true. So if we call this matrix R, which is a kind of, I don't know, R for something, it's R for matching. It's just the thing that matches across the regions. Then this R has the following form. We can stick in a factor of K prime over K. That's just a convenient normalization. But the general form of it must be that if this is some coefficient alpha, then this must be alpha star. And if this is some coefficient beta, then this must be beta star. And that's the general form of it. And that comes directly from the fact that, you know, the potential is real. So we're using that symmetry in order to constrain the form of this R. We also have, so that's one constraint. So what we're doing here, we're just trying to make the matching as simple as possible, where we don't have to solve for all these coefficients. We're just, which, you know, would involve calculating every single element in here. We're trying to use the symmetries of the potential and probability conservation, as we'll see, in order to reduce this problem down as far as possible, so that we only have to determine maybe like one or two complex numbers to figure out the whole solution for the scattering problem. So that's the idea. Okay, so we have that, and the other thing we have is current conservation. You know, the amount of particles that comes in has to be equal to the amount of particles that get transmitted through, and the ones plus the ones that come back and get reflected. So there's probability current conservation, and that tells us that what? That K, right? Remember, this is the momentum piece, and now it's A squared minus B squared. That's the incoming minus the reflected portions, right? That has to be equal to K prime. This is in the interaction zone. And since this is, we'll see later how we can eventually ignore this region 2, but for now, you know, there's going to be incoming and outgoing in region 1 and incoming and outgoing, you know, left and right moving things in region 2. So if those have to match, the probability currents have to match. So the ones going to the left minus the ones going to the right, the currents, they have to be the same in region 1 and 2. Maybe it's better to put, you know, like left and right moving things. This is the current moving left. This is the one moving right. This is the one moving left. This is the one moving right in regions 1 and in region 2. And remember, our region 2 here is a simple one where it's just, you know, like a constant potential. So, and you have to have this K prime here, right? Because it's got a different kinetic energy in that region 2, but it's just flat. So. But we'll see. We're just doing the scattering problem how we would do it brute force, but we're using this matrix, which we'll see makes life a little bit easier. So what does it mean? It means that we can rewrite this thing actually. Well, what can we do? We have this matrix R, right? And the R tells us how to connect C and D and A and B. And we know R has this form. So we can write C and D in terms of A and B. You can use the R matrix now. And this whole thing is going to be equal to what? K, and then it's going to be K prime over K. Let's see. So I guess, yeah, it's better. So we have A and B here, right? And that's what, and okay, let me write it out here. We have A and B is equal to square root of K prime over K, right? Alpha, beta, beta star, alpha star, all that acting on C, D. So we can write A as the magnitude of A squared is basically vector times this matrix, right? It's the top row. So it's C times alpha plus beta times D, and then it's the whole thing squared. So you can use the R matrix here to replace A and B with C and D. And what you get is the magnitude of alpha C plus beta D squared. That's from this top row. And then for the minus B part, what do you get? You'd get minus beta star C plus alpha star D squared. Okay, now you see why we introduced this K prime over K business, because then this cancels these Ks, and now you have just a K prime out front. And this whole thing, if you multiply it out, you can factor it actually, and it just becomes K prime magnitude of alpha squared minus magnitude of beta squared, C squared minus D squared. So if you compare this to this guy, you see this all cancels, and what you are left with is that alpha squared minus beta squared is equal to 1. So not only is the R matrix of this form, but the alpha and beta are constrained with respect to each other. It means that the determinant of square root of K over K prime, just to cancel this thing out front, times R, the determinant of that matrix has to be equal to 1. Right, because that's the determinant of this little piece here. It's alpha times alpha star minus beta times beta star. So it's even more constrained than you would expect. And okay, so then let's look at the physics of this, right? Let's look at the actual boundary condition here. So if we have a wave coming in from out here, and we just think about this region between 1 and 2, and we'll ignore 2 and 3 for now, then what we can do is actually try to do the matching, right, across the across this boundary. And so what we could do is we could substitute in, for instance, particular values of A, B, and C, and D, and see how they're related to each other. So for instance, we can look at what happens when you send in, when you, for instance, set C equal to 1 and D equal to 0, just as an example. So if we look at this boundary between region 1 and 2, and again, we have these coefficients A and B out here and C and D, we can set, for instance, C equal to 1 and D equal to 0 as a kind of choice of normalization. Just see what happens in region 1, for instance. This is where we would use the matching boundary conditions. So here we have e to the minus, so let's see, C, yeah. Or, you know, let's put D equal to 0 and C equal to 1. So this is like looking at what happens when a wave comes in from region 2 and what happens in region 1. How would we do the matching there if we have just an e to the minus I k prime x coming in here? Well, it would just be, and let's put this at x equals minus a over 2 or something like that, this boundary. So you would do the matching just as we did last class. This is a k prime a over 2, and this has to be equal to a e to the, oh, let's see, I've flipped these. Yeah, I k a over 2 plus b e to the minus I k a over 2. Oh, no, this is minus, okay. Oh, no, sorry, this is all correct. So this is, we're setting C equal to, we're setting C equal to 1 and D equal to 0 and evaluating at x equals a minus a over 2, just as a matching point. All right, this is a minus a over 2. So minus a over 2, you get this for the C portion, there's no D, and then this is for these guys. You would also get from the derivative, so this is from psi of x, from the derivative of psi, that matching condition, you would get k prime e to the minus I k prime a over 2 is equal to ka e to the minus I k a over 2 minus kb e to the I k a over 2. The point here is that you can choose whatever normalization you want to get these coefficients that you need in order to determine the properties of your matrix. Right, so in this case, we chose this normalization. Why did we choose that? Because remember that our R matrix here connects A and B and C and D. A and B to C and D. So the reason we chose it is now what do we know? We know that A and B, right, acting with this R matrix. And if we set C equal to, if we do this, right, which is what we're doing with this matching, then we conclude, right, that A is equal to, well, let's write out what it is. It's, you know, square root of, here we have it up here, square root of k prime over k, alpha star, beta star here, and it, you know, it's well, we just write it again, 1 0. So that means, right, A is equal to what? It's this vector multiplied by this guy. So it's the top row here is just square root of k prime over k alpha, right? And then B is square root of k prime over k beta star. So that's what we're doing here. We're just trying to figure out these elements, alpha and beta star, by choosing a particular boundary condition. In this case, C equals 1 and D equals 0. And we could do the matching, right? And we do the matching by matching the derivative and the function. And now you have two equations, right, and two unknowns. So you can solve these for A and B. And that immediately gives you what alpha and beta are, because, you know, that's what the R matrix does. Just encodes the matching condition. So you combine these two things, right? And I'm not going to do the algebra here, it's a little bit tedious, but in the end, you get that alpha, right, is equal to what? K over K prime A and I can use these two equations to solve for A and B in terms of, you know, the e to the I, k, and k prime. And what you get is a kind of, you know, it's relatively gross expression. You'll be practicing solving these kinds of algebraic equations on homework. I just don't want to do the algebra on this. Yeah, you could stick it in the Mathematica, give it these two equations, two unknowns. They're, you know, linear equation. It's not, you know, it's just solving this one for A, substituting in, and solving, you know, for B, and so on. So that you get e to the I, k minus k prime, A over 2. And for beta, you get k minus k prime over 2 square root of k prime, the I, k plus k prime, A over 2. So now what? Well, now we have this matrix R, and we have fully worked out what the elements of that matrix are. And you can even check that, you know, this satisfies that determinant condition. This guy, alpha squared minus beta squared is equal to 1. And now what we want to do is do the same thing, but between region 2 and 3. Do the same kind of matching. And what you find is you can basically use the symmetry of this particular problem to argue that, so what do we want now? We want a connection, right, between C and D. And now I'm going to call this R tilde, a new matrix, C and D, and, you know, F and G, right? That's between regions 2 and 3. You can do the same kind of matching. You can go through the same business of making arguments about, so yes, connecting C and D and F and G. You can go through the same business of making arguments about current conservation and using a particular boundary condition. Just this is a choice in order to make the solution for A and B easy. In this case, for the solution for like C and D, you could set F equal to 0 and G equal to 1 and work it out, for instance. What you find is, because of the symmetry of this particular problem, that, you know, this is exactly the same as before. First of all, you know, first of all, this thing has the same form. It must, just by the fact that the potential is real and current conservation, must have the same general form in terms of these beta, alpha and beta coefficients. I put a little tilde because it could be a different beta from the boundary between 1 and 2. But it still has the same form. And you can show that for this particular potential step, the potential, well, because it's so symmetric and the boundary between 1 and 2 is symmetric, the boundary between 2 and 3, that this thing is actually just looks quite similar to the R matrix, except the off diagonal pieces pick up a an extra star and a minus sign. But other than that, it's pretty much the same. So then, now what? Now you have a connection that connects between A and B, right? A and B and C and D. And then you have another connection that connects between C and D and F and G. So you can combine that whole thing into one matrix and connect up A and B via R and R tilde to F and G, the asymptotic states. These are now in regions 1 and 3, right? And kind of all of the stuff that went on in region 2 is encoded in this matrix, because we matched at, you know, in the boundary between 1 and 2, and then we matched between 2 and 3. And so this whole thing, we can call it matrix M. And it connects the coefficients of the incoming and outgoing waves, you know, at plus infinity, and the incoming and outgoing waves at minus infinity. Does that make sense? Just the general scheme of this. So now we're going to talk about this matrix M.
I think it'll make more sense when we go over that algebra that you skipped, you know, or at least I do. So at least for me, because I can see what you're saying, you know, all it is just steps, you know, all we're taking is just, and we're assigning those easy to solve, you know, set it to 1 or 0. And
Yeah.
so it stays, which makes sense. That's how you would do things, you know, when I was studying this in undergrad, you know, we'd set it to 1 or 0 or something. But I think I have to go through the algebra in order to see a little better because I was following you, but that algebra helps me, so I'll have to do it.
Okay. All right. Yeah, I mean, it's just, yeah, that's right. I might do some in recitation then for some of this stuff. Okay, so the connection here also, remember that the one connection, so again, just to remind you, this is matching between 1 and 2, right? The connection here, see, there's a K prime over K, right? And that's the K prime was in region 2 and this is in region 1. It's flipped for between region 2 and 3 because region 2 now is the one that's on the left and that has K prime, and region 3 is the one that's on the right and that has K. So when we multiply these two matrices together, R and R prime, those little normalization things cancel out the square roots of K over K prime. This cancels, you can see my mouse, right?
Yeah.
Like okay, so this K over K prime gets canceled when we multiply by K prime over K up here in the definition for R. Okay, so the whole matrix then, this whole matrix M has the following form. It's some, if you multiply it all out, it's got gamma star, and these are related to the alphas and alpha tildes. And then it's got delta and delta star. That's the general form. And it also has the same alpha squared minus beta squared equal 1 condition. In this case, it just, that's the kind of general form for the matrix. And so you see, we reduced kind of the whole scattering problem to determining just 2 complex numbers, this gamma and this delta. So that's kind of interesting and impressive that we took this very complicated problem and reduced it to just the determination of 2 complex numbers. We can also do more and use different properties of the potential. Say the potential is even. Then we can use that symmetry in order to constrain this equation even more. This equation between A and B and F and G. So see, what else should I say about that? Yeah, and of course you can prove all this kind of independently, right, of this R and R star. What you do is you say, well, there must be some connection between A and B, right, and F and G. And you can still use current conservation and the fact that the Schrodinger equation, you know, is the solution to it. You can complex conjugate any solution to it and still get a valid solution. You can use that, and from that you can again conclude. So again, you use psi star as a solution, and you use the fact that well, now the current conservation is easy, right? Because you need the stuff that's coming left and right. Now they have the same K, right? Because these are now the asymptotic regions. So you have to have this that constrains these M1s, M2s to be of this form. So that's not a way you can think about it without, you know, going through this business of R star or R tilde if you want. Same kind of deal, right? It's still solving the Schrodinger equation. You're just bypassing this region too. Okay, but this is the main point, is that no matter how you think of it, either as a product of these two matrices or as an individual sort of connection between region 1 and region 3, this is the constraint that it has to satisfy. Okay, so let's try to use even potentials, right? In order to understand what's going on when we have an even potential, and see if we can get any more constraints on this M matrix. And you can, because if we have an even potential, then psi of minus x, right, is also a solution to the Schrodinger equation. And so what that means is if we do psi of minus x, right, then the A and B and F and G regions, they flip, right? Because everything at plus x becomes stuff at minus x. And so it means that you also need, and of course, the little e to the I kx's, if you take minus x, they flip signs. So the direction of the particle, whether it's going left or right, that changes too. So what does it mean? That means the A, which is like coming in from the left in region 1, becomes coming in from the right in region 3. So this A becomes a G. This B becomes an F. The coming in from the right in region 1 becomes coming in from the left in region 3, which is F. So this, and it must be the same matrix, this has to be equal to this. So now you have two conditions on your matrix. It not only connects F and G, but it also must satisfy this reversal due to the parity invariance. And so you can figure out that you can figure out things like, well, you can take the inverse of this matrix, right? And then you'll find that BA is equal to the inverse acting on GF. And we can actually, since the 2x2 matrix, you can actually work out what the matrix inverse is for an arbitrary sort of 2x2 matrix that satisfies this determinant condition. What happens is that you get the diagonal pieces flip, and these pick up a minus sign. It's just constructing the inverse of a 2x2 matrix. Maybe I'll show that in recitation too at some point. But you can take any 2x2 matrix and invert it. It's 1 over the determinant, but the determinant here is equal to 1, so that part doesn't matter. And then what you do is you flip these two guys, and then you add little minus signs on the off diagonals, and that's how you construct the inverse of a 2x2 guy. Maybe I'll show you. A11, A22, A12, A21. If you want to invert it, it's 1 over the determinant of the matrix, and then these guys become A22, A11, and these pick up a minus sign. You can check that it works. You can take this matrix, multiply it by the original thing, get the inverse. So, it works as long as the determinant doesn't vanish. For us, the determinant doesn't vanish because it's 1, so it's fine. All right, and then this whole thing is acting on GF. And now we just compare that, right, to this original thing that says that AB is equal to, M11, M22, M12. M21, just the matrix elements, FG. And now we can compare, right? This connects A and B to F and G, and so does this one. And so these both have to be satisfied. And what we can conclude is that M12 is equal to minus M21, and that, but we also know that these off-diagonal ones are complex conjugates of each other. So we also have that M12 star is equal to M21. And the only way that this is possible where they're complex conjugates of each other and they satisfy this relationship where they're negative with respect to each other is if they're pure imaginary. That's the only way. So M12 is pure imaginary. That's the only way these two conditions are satisfied. So our general form for the matrix M for an even potential has to be gamma star. That doesn't change, but these become pure imaginary and complex conjugates of each other like this. So see, they're differing by a minus sign and they're complex conjugates of each other, which is what happens when you have pure imaginary. So now I wrote it in this way where eta is real now, right? And the off diagonal thing is pure imaginary. And there's this constraint that comes from the current conservation that this is equal to 1. So really nice. Now, what did we do here? We used the fact that the potential is symmetric like this and using just these matrix ideas to derive a constraint on this connection between the regions 1 and 3. And we reduced our problem to now not only just determining here, okay, you have to determine 2 complex coefficients. That's 4 parameters, the 2 real parts, the 2 imaginary parts. So that's 4 plus this constraint, so I guess 3 parameters that you'd have to determine, 3 unknowns. Now, after this, using this symmetry, if we have an even potential, we reduce the problem down to determining a real number and a complex number. It's 3 parameters and 1 constraint, so that's 2 parameters. So you just have to determine 2 different numbers, right? They're just real numbers. And that's a lot easier than going through the whole process of matching coefficients that, you know, we sort of started with over here. A, B, see, we started with all of these guys, which are complex numbers. And man, you know, there's 1, 2, 3, 4, 5, 6 of them. So that's a pain. That's a pain to do, and it's nicer to think about it as the matching conditions is a kind of matrix multiplication where you're connecting coefficients in the different regions. And you can use symmetries in order to constrain those matrices that connect the coefficients. So that's the point of what we're doing. Any questions about that? I'll probably do an example in recitation related to this, actually calculating an explicit M, but I think I'll leave that alone for now. And I wanted to mention briefly about the S matrix. So M is a little bit inconvenient in that if you think about what it connects F and G to A and B, these 2 regions. But if you're thinking about the physics of the problem, right, what we really want to connect is particles that go into the interaction region and ones that come out, right? It's sort of, that's how we would think about it in 3D, right? We have some interaction zone, and then we have things that come in, particles that come in here and interact, and then ones that come out after they have interacted. And in 1D, it's not really regions 1 and 3, right? It's different, right? In region 1, we have things coming in from the left. That's coefficient A that goes in. And in region 3, we also have stuff coming in from the right, from out here. And that's coefficient G. These are the in states. And then there's out states. The out states are the ones that, you know, the reflected portion in region 1 that goes out here. That's this guy that goes out. And in region 3, we have the stuff that comes out that gets transmitted, right? That's the F. That's the out. And so what the S matrix tells you is the relationship between the in and out coefficients, the in and out states, stuff you're sending into the interaction zone, the stuff that comes out, and the stuff that comes out is, either the reflected or the transmitted part in the 1D case. In 3D, if you think about it, it's a little bit more symmetric, right? You send stuff in and stuff comes out. And so, that's all you have. You don't really have reflection and transmission in that sense. So in order to connect this 1D stuff to what we'll eventually do for 3D next semester, for the most part, it's nice to introduce this S matrix. It's just like the M matrix, except it connects the out states, B and F, to the in states, A and G. So you have stuff that comes in, these coefficients, and the S matrix acts on them and gives you the stuff that comes out. So it encodes, right, the interaction, right? It encodes the interaction in region 2, or in the interaction zone, if you want to think about it, in the 3D case. Interaction region. You send stuff in, and remember what we usually do is we set G equal to 0, right? Because we don't have anything coming in from the right. We just have things coming in like from the left. And what is the S tells you what B and F are, and B, remember, in the 1D case is the reflected part, right? Reflected amplitude, and this is the transmitted one. So S encodes what the interaction does to the incoming wave. And you can figure out what it is in terms of the M matrix if you want, but we can use symmetry again. So what about current conservation? Current conservation tells us what? Well, it tells us that the stuff coming in, right? Now that all the signs are going to be correct. This is all the stuff coming in has to be equal to the stuff that comes out. And what does this mean? This means that the magnitude of this vector must be the same as the magnitude of this vector. So what can we conclude about S?
Well, then it's the same as M, right? I mean, if it has to be the same, right? I mean, since you're following it, is that what you just said?
No. Well, M connects F and G and A and B, which mix up the in and out states. They have a different condition on the F and G. It was this condition. So this vector does not have to have the same magnitude as this one. But for S, the way it's written, it means that the magnitude of this vector has to be equal to the magnitude of this vector. So what can we conclude about S? What kind of matrix is it?
Unitary?
Yeah, that's right. It's a unitary matrix. And of course, in finite dimensions, it's sort of would be obvious. Infinite, it's a little work, but anyway, it's true though that the S matrix is always unitary. And there's another thing. We can use the complex conjugation part. Remember that we used current conservation and the fact that psi star is a solution to the Schrodinger equation. And if you want to get technical, the symmetry associated with that is time reversal. We might talk about that next semester a little bit, I don't know. But it's time reversal symmetry. The physical situation of having a scattering event. If you play that movie backwards in your head, that's still a valid physical situation for the problem. So Schrodinger, the time evolution, according to Schrodinger equation, is time reversible. In that way, the time reverse solution is also a valid solution. So in that time independent case, the equivalent to that is that psi star is a solution to the Schrodinger equation.
So go back to the S matrix though. You're saying both for infinite and finite, it is always, no matter what, unitary.
Yeah, well, we are in infinite dimensional Hilbert space, right? Because it's
That's what I
So
thought we
looking
were
at
studying,
space
but
of
I mean,
space
but
of
you did
wave
say
functions.
finite though. And that's something we can
It's
prove
unitary.
though.
I mean, yeah, and it's unitary. It gets okay. So it's finite dimensional here in the sense that it connects these coefficients. Our
Mhm.
Hilbert space is infinite dimensional for even for 1D scattering. But yeah, I guess I mean in this case this is two-dimensional problem since it's just connecting these coefficients. In principle, the S matrix is also valid in it is a valid is a reasonable concept in field theory, and there you would have an infinite dimensional set of coefficients effectively. But we'll see that later towards the end of the second semester. But you can forget about that for now. The point is current conservation gives you this. That means this vector is the same as this vector. And so S is norm preserving. And so, it must be unitary. And it has another constraint that since psi star is a solution of Schrodinger equation, that means, again, we have this reversal. So the out states, if we star them right, then they become stuff that's going in reverses and it becomes stuff that goes out. So A star, G star has to be equal to S B star, F star. Right, when you complex conjugate the wave function, if you think about the e to the ikx's associated with that, they all flip signs. So if you have stuff that's coming in, it reverses direction, becomes stuff that's going out. So the in states become the out states and vice versa. So you replace A and G with B and F star, and B and F becomes A and G star. You just reverse them. That's how you can see it's related to time reversal symmetry, because in the time reverse situation, you play the movie of scattering back in your head, you have stuff that came out going back in, right, interacting, and then when it comes out, it's time reverse, so it's going out when it was coming in before. It's sort of, you can draw a little space-time diagram, right, of scattering. You have things coming in, interacting, and then they go out. If you time reverse it, right, you run time backwards in your head, then the stuff that came out is now the stuff that's going in, and the stuff that came in is now stuff that's going out, right? It's in, out, time reversed, T star minus T. The out becomes the in stuff, like that. So it means that S has to satisfy this too. So that puts pretty strong constraints on it. It means that S has to be equal to S star inverse, because if we take the star of the original equation, right, we get B star, F star, S star, A star, G star. So S has to S star has to be its own. S has to be the inverse of S star, right? Because if I substitute in for B star F star here, I would get S star, A star G star. So this thing must take A star G star back to A star G star. So this has to be equal to the identity, right? So the only way that will work is if S star is the inverse of S. Okay, and so that puts some pretty strong constraints. It means that we can, of course, exchange the inverse in the complex conjugate, and we know that S is unitary, so the inverse of S is S dagger star, right? This is unitary. And moreover, what's a dagger? It's a transpose in a complex conjugate. So it's a transpose, and then you take two complex conjugations, which just undoes the complex conjugation. So this is ST. So not only is S unitary, S is symmetric. It's a symmetric matrix. not Hermitian, but straight up symmetric. It's equal to its transpose. Yeah. Okay, any questions about the S matrix? We'll see more of it when we do 3D, but this is a teaser of it, of what it looks like in 1D. Connects in and out states. We can use symmetries of the potential, and especially we can use current conservation and time reversal symmetry to really constrain any scattering problem down to just a few coefficients they have to determine. And those you would, determine by matching boundary conditions and actually, figuring out properties of the interaction potential in that region too. Good.
I think so. As long as you follow those rules you just told us, it's pretty straightforward, actually. But actually applying it to something realistic would probably not be.
Well, I mean, for the most part, applying it to something realistic just involves doing the actual matching and stuff that I did in class last time, or I did in recitation. But I really think that's best for you to work out yourself, because I mean, it's algebra at that point. It's not really conceptually interesting. The interesting thing conceptually here is that there's a unitary matrix that connects the coefficients that you're matching. You can think of it as a check. You do this problem, you do a scattering problem in brute force, right? You like find all these coefficients by matching the derivatives and so on. You do all this stuff, and you get some really ugly answer, and they will be quite ugly in general, very complicated expressions. And I mean, that's useful. I guess you can plot it and figure out probabilities of transmission and reflection, but it's sort of, it misses the conceptual point that these coefficients are actually very constrained. The symmetries of the problem constrain the answer that you get quite a bit. That the connection between them is just given by a few parameters that will depend on the details of the potential, but that's not so important. I mean, it's amazing, right? You reduce any complicated potential, it's like some crazy wiggly thing, you can reduce it to just the value of some coefficient. As we showed, the whole scattering problem reduces to determining this relatively simple 2x2 matrix, just a function of a couple of coefficients. And that's the really important thing, is that symmetries or conservation laws, like probability conservation and time reversal symmetry in this case, really strongly constrain your scattering problem. And originally when field theory was being developed, this kind of approach of where you reduce solving the problem to determining the constraints on the solutions using symmetries, and in particular for particle scattering, this S matrix approach, it was kind of viewed as an alternative to the field theory approach. It's historically interesting, but we'll talk more about that in the second semester, I guess, towards the end. Okay, so the last bit I wanted to talk about today, I'll still start it and I'll finish it next time, is the harmonic oscillator. And that's us solving the harmonic oscillator potential, which is, our friend, the parabola potential. And already we can use our intuition about what we know, right? If we put an energy here and we try to look for our, energy eigenstates, what do we know? I mean, this is a parabola, it goes out to infinity. So at some point there'll be some places where E crosses the potential. So we know that we'll be looking for, bound states, which vanish at infinity because the particle is forbidden to go beyond here classically. So it has to sort of tunnel in. So you have something like exponential decays. And in here, it'll have some kinetic energy. It'll wiggle around. So we're looking for these things. And we know from our intuition that if you have a bound state and you constrain things out here to vanish, we'll have an extra constraint that we can't satisfy for an arbitrary E, we'll have the situation that these will be discrete values, because the potential just goes up to infinity, so it confines the particle inside, and so you're only looking for bound states. There are no scattering states here, and so we expect then that over-constrains our eigenvalue solutions, eigenfunction solutions, to particular values of the energy. And in this case, it's actually easier to not work with the functions, but to work with this guy, the actual operator itself. And the place where we begin is rewriting this. So this is the spring constant, if you remember. It's just the mass on a spring. That's what this is. There's a kinetic energy, the p squared over 2m, and this guy. And it's convenient to rewrite this thing in terms of slightly different variables. So you have the momentum plus 1/2, and it's convenient to rewrite the k as m omega squared, where omega is the classical kind of frequency of omega is square root of k over m. That's the angular frequency of it, of the oscillatory motion. And instead of x, I'm going to write q, because it could be just a generalized coordinate of some sort. And so I'm just replacing x with q. And of course, we saw that the x and p, or q and p, have to satisfy the canonical commutation relation. So first thing to do in order to try to solve, this guy, is to non-dimensionalize. It's a common theme in physics, and you introduce transformed coordinates. It's the original guys multiplied by some constants in order to kind of make q and p have the same units, is the idea. So you can rewrite things such that you can just factor out a constant that depends on h bar and things like that. And the way you do it is you introduce these hat operators, and they're just convenient transformations. They're just some constants out in front of p and q. And if you substitute these guys into here, what you get is that it's just h bar omega over 2, and it's p hat squared plus q hat squared. It's just a nice way of rewriting this guy, introducing an h bar and factors of m appropriately, so that p and q are on the same footing, so they no longer have anything out in front. And if you work out what the commutation relation is between q hat and p hat, in this case, it's the h bar goes away, and it's just that. So that's where we'll start, I guess, next time. But before I let you go here, I want to show you that all we're doing is, again, it's solving a 1D problem inside this particular potential. And if you wanted to see what that kind of looks like, you could, open up Mathematica and kind of check out what it looks like. So here is the Schrodinger equation, the time-dependent one. You got your kinetic energy, the two derivatives, plus your potential. And let's start off the function in some wave packet, with some initial momentum, e to the I kx, and then a little envelope that localizes the particle at around x minus 20. So this is what it looks like. What would we expect? We expect some mass on a spring. If we localize it here inside this potential, it should, oscillate back and forth like a mass on a spring would. We could even calculate what the period of the oscillation should be classically. It's 2 pi divided by this omega, the classical frequency, which is, so if this is k over 2, then k is equal to 0.00 25 times 2. This is square root of k. And I'm setting m equal to 1. So this is 2 pi divided by omega. And it's 88.8577. That's the time. So if I plot this solution from 0 to 88 point, the classical period, it should go through a full loop, right? And indeed it does. And this is what it looks like. It just goes back and forth. And that's one loop. And say I set it up to just loop over the one period of the motion. So it's, oscillating back and forth. And that's what we're doing here, is we're trying to solve this problem analytically for the time independent case. But we know that it's those time independent solutions, right, that give us how to solve the problem for the time dependent case, because we know that each of those time independent solutions will evolve with a little phase, right? So if you can write this wave packet as a linear combination of the time independent solutions initially, you know how the whole thing evolves. So that's why we're doing this, finding the energies and energy eigenfunctions. So yeah, I guess we'll do that next time. But I want to show you could actually just solve the Schrodinger equation for the harmonic oscillator like this if you wanted.
Could you go over before we go, because I know it's the end of our time here, the parabola that we see there in the middle of the yellow? What was that again?
That's the potential. That's the harmonic.
Okay, that is the potential, right? Okay.
Yeah.